Now we get in the meat of today's lecture. And we're going to talk about all these different advanced cache optimizations, starting with pipelining the cache. OK, so here is our sketch of what happens in a cache. In a cache, we have a tag, and we have the data blocks here. And we want to go do write into the cache. So forget about the read for a second. But instead, let's focus on the write. So in the write, you're going to do a tag check. So you're going to index into here with the index into your tag array. It's going to spit out the tag. You want to check the valid bit also. And you're going to do a comparison here. If it matches, that means that the data is already in the cache. And you're doing a write. So you can just write the data into the cache. So that sounds good. Some challenges here is it really is sequential. You need to absolutely do this first before you do the write. Because if you have a different address stored in this location here, and you just blindly do the write, you're going to overwrite the wrong data. And then you're just going to be very unhappy because you overwrote some data which wasn't apportioned to this, this particular write, or was at the wrong address. So that's definitely a bummer. So do we think we would want to try to do this in one cycle? Anyone want to wager a guess here? Do people build machines where they do this in one cycle? Well, sure. Original machines did do this in one cycle. It's possible to build. You have a nice combinational path that sort of comes through out of the index, through here, through all this logic, and then through the write enable into here. It's buildable. Not great for your clock performance. So the first optimization, so how do we reduce the hit time for a write? And there's a couple different strategies to this. So we can think of this as trying to do this over two different cycles. The first cycle checks the tag, we'll say. And the second cycle does something to the data. That's kind of our problem statement. What are our solutions? One solution is kind of innovative, is you can build a multi-ported cache, or a cache which can simultaneously do a read and a write to the same address. And you do that. So you have a cache, you're doing a write. You blindly do the write, not checking the tag. But at the same time, you read the old data that was there, and you save it off. And if you took a tag miss for the write, you go back and actually fix it up by filling that back in. That is an option. People have built such things. So you just restore the old value on a tag miss. Works perfectly fine. You need a side buffer. This kind of looks like a victim cache, which we'll talk about later in today's lecture. But you can do a write and a read at the same time. And it's kind of like you're putting the new data in speculatively, pulling out the old data, the victim. And if the write hits in the tag check, then you just let it go and everything's great. If not, you have to basically pull that back out and undo it. It's doable. Not a lot of people do this, but people have built machines like that. Another solution is trying to build a fully associative cache. Now, what do I mean by a fully associative cache? Well, I mean a cache which has lines such that you can store to any location in the cache. And in those structures, typically the tag check and the access are kind of done in parallel. So because you don't know where to find the data, there's no index operation. The index operation is the tag check or the CAM operation or the content addressable memory operation. You're basically doing it in parallel. So, or you're basically doing the tag check to do the read anyway. And it doesn't really hurt you to sort of do the tag check first and then do the write. So it just doesn't really hurt you. It's not necessarily a great design if you have a very large cache. But for a small cache, you can definitely have a content addressable memory for the tags, and then just have it so you can write anywhere if you have a fully associative cache. That is one way to solve this write problem. And then we're going to look at, but this is what we're going to focus on in today's lecture, is pipelining the write. So to pipeline the write, instead of actually doing the write in the cycle, in the M stage of your pipeline, we're going to do the tag check in the M stage, and then hold the store data for some time in the future. Now you're going to say, did we actually do the store then? Well, yes, we're going to call that committed state. So this is what we're going to focus on today, is how to do a pipelined memory access to reduce our write hit time. So here we have our 5-stage pipeline. And what we're going to do is when we get to the M stage for a write, we're going to check the tag, and we're not going to fire up the data array at all. Now you might say, where do you put the data? Well, we put a nice little buffer here, which is a basically to be stored buffer. It stores the data that's going to be stored in the future, or a delayed cache write buffer is what we'll call this. So in parallel, you check the tag, and you store the data here. And then, sometime in the future, you want to move this into the cache. But you need a convenient time to do that. So one option is you wait for a dead cycle on the cache. OK, that sounds good. How do you know you're going to get a dead cycle? I can't guarantee that. I can write a piece of code which does store after 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 store in a really tight loop. So you'll never have a dead cycle. A cool little trick here is a subsequent store only has to use the tag array. So if you have a store after a store, the first store we'll check the tag and not use the data. We'll store the data here. And then when the second store comes down the pipe, it'll check the tag, but the data array is open. So you can do the store at that time. So it's a cool little trick there. If you have a store after a store after a store, you can basically decouple the tag from the data for stores and use the port on the cache to do the data array of the cache to do the store later. And we can look at this with a little bit more detailed drawing here. And this is just kind of to reiterate what was going on. You do the store, it checks the tags, and it's going to store the address and the data. And at some point in the future, when there's an idle cycle or another store going on, it'll actually transition this data into the data array. That sounds good. OK, so pop quiz question here. What happens when you do a load and there's data in the delayed write data buffer? You have to bypass it. Yes, you need to go check it. So you need to have something which is going to check, and that's actually drawn here, the delayed write address against a future load. And if you get a hit there, you need to have this data come around and come out. So we basically need to go check this buffer. One thing I did want to point is this is kind of the naive way to do this. More advanced processors will actually typically have a multi-entry version of these delayed write data buffers because caches are sort of usually pipelined inside the cache too. It might take multiple cycles to actually access the data array. So you might not do this till the end of the pipe. So some of the processors that I've worked on, these are sort of on these delayed write buffers are sort of in the order of maybe 2 to 4 entries big. So you can abstract this and make this into a bigger data structure. And when you do loads, you obviously have to do a content addressable match against all of those entries and see if the data is in the delayed write data buffer. OK, so let's go see how well this does. Pipelining our cache. We're going to use this throughout today's lecture. Ways that it makes life better. You can either reduce the miss rate, so do something good for miss rate. You can either do something good for reducing the miss penalty. You can reduce the hit time. And this would be like, for instance, having a smaller cache reduces the hit time. Or you can increase the bandwidth to your cache. But all these things are going to factor into performance. And not all of the techniques, the optimizations we're going to talk about today, touch all of these. In fact, most of them only touch sort of 1 at a time or 2 at a time. OK, so pipeline caches, what do they do for us? Are they going to reduce the miss rate? I see people shaking their heads no. Yeah, we didn't make anything bigger or smaller here. It's probably not going to touch the miss rate. Is it going to affect our miss penalty? So this is when we miss in the cache, how long it takes us to go to, let's say, the main memory or the next level of cache. No, it's not actually going anywhere different. Effectively, this is implementing the exact same thing. Hit time. Does this affect the hit time? Well, it's going to affect the hit time. It's kind of hard to see whether this does it in the positive or negative direction here. If you compare to having the, let's say, tag access and data access all in the same cycle, pipelining is actually going to make the hit time a little bit better because you're doing less in a cycle. So that would have us put a plus here. But if you compare to, let's say, not having a cache or just having a big RAM there, it actually makes the hit time worse because we need to mux in multiple extra stuff here. We need to basically do this extra check. We need to do the associative check against our delayed write buffer data. So that actually hurts us a little bit there. So, OK, that might be a plus or a minus. The bandwidth, though, is actually going to be better through this cache. Because before, we had to just sort of wait for this cache for, let's say, the whole time to go through the tag check and the data check, and the data write. But now we can actually have 2 stores sort of happening at the same time, or the tag for one store and the data for a different store. So this is really going to make the bandwidth better for this. So that's where we are with pipeline caches.